Okay, so this will be the last part of our chapter 1. So we have already differentiate units and dimensions earlier in part 2. Also, I have introduced there the unit systems that we might use later as we go along on fluid mechanics, which is the SI, the USCS, and the PG system. So now, let us proceed to the topics and dimensional analysis, or sometimes I denote it as unit analysis. So this section introduces dimensionless groups, the concept of dimensional homogeneity of an equation, and a process for carrying and cancelling units in a calculation. So this knowledge is useful in all aspects of engineering, especially for finding and correcting mistakes during calculations and during derivations of equations. So unit analysis is really useful, guys, a useful tool later. Okay, so as we go along with our topic in fluid mechanics. So in unit analysis, we have these dimensionless groups. So what is a dimensionless group? So it is any arrangement of variables in which the primary dimensions cancel. Okay, so that is the keyword there. Okay, so cancel. Okay, so for example, considering a pipe with an inside diameter and length L, so these variables can be grouped to form a new variable, which is an example of dimensionless group. So specifically, if we make a ratio between them, okay, ratio between the inside diameter, okay, so ratio of inside diameter over the length, okay, so that would really cancel out, okay, since say the unit for diameter, inside diameter is in mm, then length is also in mm, then this will be cancelled out. Okay, so therefore this will be considered as dimensionless group. Also, another common example is the Reynolds number. The Reynolds number involves density, which is with this sign here, this row here, density. This V here is the velocity, then L is the length, and mu is the viscosity. Okay, so R is the Reynolds number. Okay, so we are tasked here to prove if this Reynolds number equation is really in the dimensionless group. So we have to work out the variables here. So variables, so we have this density, this velocity, the length, the viscosity. Then we will analyze the primary dimensions as we have discussed on part 2. So density has this unit or rather dimension, which is a mass over cubic length. Then for velocity, we have this length over time. Then this length here represents length L. Then viscosity is equal to the mass over the length times time. Okay, so what we will do is simply substitute these dimensions, these listed dimensions, to the equation. Okay, so we will try. Okay, so density, so we have this mass over cubic length. Okay, cubic length, then times the velocity, so length over time, then length, so L, then over viscosity, which is m over LT. So what we can see here is the reciprocal, this equation here. So that is the reciprocal of the denominator, which is m over LT. So as you can see, we have this m dimension here at the top. Okay, so we have this m. So I also have this m at the bottom, so we could cancel out that dimension. Then L cube. So if we multiply this 3 L here at the numerator, L times L times L, so that will also give us L cube. Okay, so L cube cancel out. Then we have this time at the denominator, and also this time here at the numerator. So therefore, we this dashed line here indicates that Reynolds number belongs to the dimensionless group. Okay, so that is a basic sample for dimensionless group. Now let us proceed to dimensional homogeneity. So when the primary dimensions on each term of an equation are the same, so the equation is dimensionally homogeneous. So for example, considering the equation for vertical position S of an object moving in a gravitational field. So I think this is common equation of the vertical position S. This is from your physics or from your dynamics. So this S position here, so say we have this dimension length, say this is a length. Okay, so that position is a length. Then G. Okay, so we all know that G has a dimension of length over time squared. Okay, that is for G. Then for time, since that is time squared, so we denote that as T squared. Okay, so if we substitute this dimensions in our equation here, so we could cancel out that LT squared then times T squared then over 2. So that is T squared cancel out. Okay, T squared cancel out. So the only dimension that we are left here is L. Okay, so this also has a L here. Okay, so the same with this, as we all know that velocity is length over time. Then we have this T here, so T, so times, so length over time to cancel out time, so the dimension left here is L. Okay, so L. Then S is also L. Okay, so there's a homogeneous dimension here. Okay, for this equation in each term. Okay, so that is dimensional homogeneity. So next example is for ideal gas law. So given by P is equal to rho times R times T. Okay, so primary dimension for the first term. So basically that is for this P here. Okay, so that is our first term. So that P has that M over LT squared dimension. Then second, for the second terms, so which are the density. Okay, so density is mass over length cube. Then R is equal to length squared over theta, T squared, or theta is the temperature. Okay, and T is the is equal to theta. Okay, or temperature. So R here is the gas constant. Okay, so if we substitute all these primary dimensions in the given equation, okay, given equation here, then we could get the same. Okay, so for P, M over LT squared, so substitute rho, then this is R, then this is for T. Okay, so theta of denominator and numerator, so cancel out. So L squared, so cancel out L squared, so what we have left here is L. What left here is L. So the result for that is M over LT squared, which is homogeneous with P. Okay, so M over LT squared. So we conclude that the ideal gas law is dimensionally homogeneous because the primary dimensions of each term are the same. So we also have this grid method. So because fluid mechanics involves complex equations and traditional units, so which are the SI, USCS, and BG system, this section presents the grid method, which is a systematic way to carry and cancel out units. So we have this example here. So maybe we are tasked here to get the power. Okay, so to get the power in watts. Okay, so that is a typical unit of power in SI. Okay, in watts. So say we have this given F here. So this is our F. F is equal to 4 pound force, or that is a force, then times the velocity. So our velocity is 20 miles per hour. Okay, so in order to convert that, so we'll be using the basic conversions such as this. Okay, so we are tasked to cancel out, say, pound force. So in SI, 1 pound or 1 newton is equal to 0.2248 pound force in USCS. Okay, so that is the conversion. Then for miles per hour for the velocity, so in SI, so 1 meter per second is equivalent to 2.237 miles per hour. So miles per hour is the numerator, then also denominator, so we could cancel it out. Okay, so what we left here is Newton. Okay, so what we left here is Newton and meter per second. So Newton times meter per second, and Newton meter per second is equal to watts. Okay, so our answer here is the power is equal to 159 watts. Okay, so that is the grid method. So this is the common method that we use when we are converting from one unit system to another. So there's a step here, okay, to apply the grid method in these two examples. So the first process step is to write the problem. Okay, to write the problem. Then second, conversion ratios. Then do the algebra. Then the calculation. Okay, so such as this, say in our example 2. So find the force in newtons that is needed to accelerate a mass of 10 grams at a rate of 15 feet per second squared. Okay, so given mass and given this acceleration, so we are tasked to look for the force. Okay, so that is force is equal to mass times acceleration. So we will convert the mass into kilogram. Okay, so in order to convert this, we all know that 1 kilogram is equal to 1000 grams. Okay, then also we are tasked to convert feet. Okay, so since we are not consistent with our unit system, so since our mass is in SI and our acceleration is in USCS. Okay, so we'll jump here. Okay, so we all know that in every 1 meter there is a 3.281 feet. Okay, so we'll convert feet into meters, then a kilogram. Okay, so 1 newton second squared over kilogram meter. Okay, so kilogram here, then cancel out kilogram, squared, cancel out, then feet, cancel out, then meters, then meters. So what we have here is a force which is equal to 0.0457. Okay, so that is the force that we get there from example 2. So this is the end of chapter 1 or part 3.